All right, we're back with limiting reactant. Now that we kind of know what stoichiometry is and how to use the ratios, finding the limiting reactant is the most important thing for you to be able to do. As I mentioned before, it is where you will start all the other types of problems. Your excess reactant, your theoretical yield, all of it begins with your limiting reactant. So I know not everyone works these problems the same way. Different teachers have different ways to approach this. So I'm going to show in number one the way that I know many teachers teach this, and then I'm going to, in number two, show you how I work it, and then the rest of the video we'll be doing it my way, which not necessarily is a better way, but it's a shorter way. So yeah, that's the plan. All right, well, let's look at number one. I have a reaction here. You can see it's aluminum plus hydrobromic acid. We'll assume that's acid for now. And then in part A says when 3.22 moles of aluminum react with 4.96 moles of HBr, how many moles of H2 are formed? Well, you might right away, let's back up a half a step here. Before I can answer part A, I actually have to figure out part B first, and we're going to do that. So this goes kind of into the different ways to do this. I can use hydrogen as sort of my guide for what's limiting and what's excess. So this is method one, and this is figuring out, there's no real proper name to this. Method one is finding yield from each reactant. So we're going to find out the amount of hydrogen that we could make from each of the reactants. All right, so let's start with, now I'll go back to what I was going to say before. You might right away think that aluminum is limiting because it's 3.22 moles, and that's less than 4.96. It doesn't work like that. The reason it doesn't work like that is because the ratios are not 1-to-1. If the coefficients of both of my reactants were 1, then I could just pick the smallest. That's seldom the case. So in this case, we have to work around the coefficients not being 1 and the ratio not being 1-to-1. All right, so let's go to it. We're going to start with 3.22 moles of aluminum, and we're going to calculate how many moles of hydrogen that we're going to form from this. So the ratio here, we're already in moles, so no need to prep. Let's use the ratio hydrogen to aluminum. And this is going to be from the equation a 3-to-2 ratio, which means 4.83 moles of hydrogen. So that's how much hydrogen I could make from 3.22 moles of aluminum if it were all used. All right, 4.96 moles of HBr. So now what I'm going to do is I'm going to take my other reactant and I'm going to figure out how many moles of hydrogen it could make if it were all consumed. And from the balanced equation, that is a 3 moles of hydrogen to 6 moles of HBr. And this only gives me 2.48 moles of hydrogen. So what we've got here are two different amounts of hydrogen that could be made from these reactants. This is the smaller number. So if I consumed every bit of my HBr, I could only make this much hydrogen. So that makes this the limiting reactant, and aluminum by default becomes the excess. Okay, so HBr is limiting. All right, so think about that. If you need to hit pause while you think, do so. That's very important. But like I said, that's just one way to do it. Wouldn't it be nice if I could actually somehow just look at the numbers and pick the smallest. I mentioned that that would be doable if my ratios were 1 to 1. So in my method number 2, this is my method, I'm going to do a little math trick to 1 to 1 the ratio. I'm going to fix the ratio to get it back to a 1 to 1. Here's how we do that. 21.44 moles of silicon in this reaction, 17.62 moles of nitrogen. I'm already in moles. Now, instead of finding a product, I'm going to do something very simple. I'm going to divide each of my number of moles by the coefficient. So I've done that. I've just taken each of my moles of reactants, divided it by its coefficient, and I have these numbers here. What are these numbers? Well, these numbers are the relative amounts of each reactant that I have on a 1 to 1 basis. So now, if this is the smaller of the two numbers, I know that this reactant is limiting. So silicon is limiting. So that's two ways to do it. You can use each reactant to find the amount of one of your products, the theoretical yield of one of your products. Whichever one makes the smallest amount of that product is limiting. Or method 2, you can divide the moles of each of your reactants by the coefficients from the equation. The smaller number then indicates the limiting reactant. All right, let's move forward and do a couple of other problems. Remember, I'm doing everything now my way, which is method 2, dividing by the coefficients. In problem 3 here, we're being asked the same thing. How many grams of iodine are formed? What is the limiting reactant? As I'm thinking about it, I realize I forgot to answer the how many of the product are formed in number 2, but that's okay. This video was really just centered around how to find the limiting reactant. But I'll go ahead and answer the question in part A this time. Hopefully I won't forget. All right, but we do have to figure out part B first. What is the limiting reactant? So this time the difference is I'm not starting with moles. If I'm not starting with moles, I have to prep this. I have to get to moles. So 0.56 grams of copper 2 chloride. Divide that by the molar mass. I know that's not 100% accurate because I left some decimal places off. But for the sake of time, let's live with that. So 0.0042 moles of copper 2 chloride. Let's take the 0.64 grams of the Ki now. Let's convert it into moles. The molar mass of this is 166. So that gives me 0.0039. They're really close. But let's look at the chemical equation. I can see that Ki is being used at about twice as fast, or twice as much, as the copper 2 chloride. To figure out the limiting, we're going to divide each by the coefficient. So for the copper 2 chloride, that's going to give me a number 0.0021, and this is going to be 0.00096. That's a horrible looking 9. Let's try that better. All right. So again, these numbers don't mean anything. I am just looking for the smallest, which is this one. So that tells me that my limiting reactant is going to be Ki. Let's go ahead and answer part A. How many grams of iodine are formed? Well, we always start with the limiting reactant. And the limiting reactant is this number, not this number. Sometimes after we do a step, you may see that 0.0096 come back. But the amount that we have at the beginning is this one as soon as we go from grams to moles. So that is our starting point, 0.0039 moles of Ki. And we're going to use the ratio to find iodine. So 4 moles of Ki. And then we can go ahead and multiply by the molar mass of iodine, which is, from the periodic table, times 2 to 254 grams of iodine per mole. So doing all the math to work this out, we get 0.24 grams of iodine. And that is, of course, the theoretical yield. And then finally, in example 4, I want you to work through this. I don't care which method you use. When I pop the answer up here in a moment, I'll be using mine, of course, but the answer won't change if you used method number 1. So hit pause, work through this, find the limiting reactant first, in other words, answer part B first, and then go back and calculate the grams of SO2 formed. Hit pause. All right, so if you did it my way, you got down to 0.22 divided by 4, which is 0.055, and then 0.17 divided by 11, which is 0.015. We don't care too much about what these numbers are over here, just find the smallest. This is the smallest, so my limiting reactant is this much O2. And then finally, to find that theoretical yield of SO2, I've set up the conversion factor 0.17 moles of the oxygen that's limiting times an 8 to 11 ratio, and then times the molar mass of SO2, gives me 7.91 grams of SO2. All right, so if you have any questions about this, make sure you ask. There'll be more practice upcoming, so come see me if you have questions.